kiddos, today we're going to talk more about line structures. We're going to specifically talk about formal charges and lone pairs and how to be able to interconvert those and how to recognize them so that when we see a line structure where not everything is represented, that if we had to break it out, that we know where everything is. And hopefully with some practice, you'll gain the familiarity that says, hey, I don't have to draw the whole thing out. I know, given this scenario, and the formal charge that's here, how many lone pairs there are, or vice versa, given the lone pairs there, I know what the formal charge in that scenario is going to be. Obviously, formal charges was in a separate video, so if you don't remember how to find a formal charge, you probably want to go back and look at that. So this is our simple line structure for an elementary hydrocarbon. Okay, this is butane, right? C4H10, we've got 10 hydrogens. It's saturated, meaning that there's a hydrogen in every place that there could be. There's no double bonds, there's no triple bonds, there's no nothing like that. That's what it ordinarily looks like. Remember that one of our last, sort of the magic rule for line structures is that carbons have 4 bonds, okay? So that means that even without knowing anything else, that I can look at the number of bonds on this carbon on the end, it has 1 bond there. That means that there are 3 hydrogens off of it also, because I need those 3 hydrogens to add up to 4 bonds. Well, so here's the thing. If the carbon atoms, or we're going to talk about other atoms as well, because it's more likely for them, but if the carbon atoms have charges, then that means that they don't have 4 bonds. So if there's a formal charge on one of the carbon atoms, they are not going to have 4 bonds. In fact, it pretty much automatically means if there's a formal charge, whether it's positive or negative, that carbon is only going to have 3 bonds, and then the only difference is, does it have a lone pair or not? Okay, so let's talk about the case of this carbocation. Carbocation is a term that you'll hear a lot this year. It basically means a carbon with a positive charge, a carbon that is a cation. That makes pretty good sense. So everything down at this end of the molecule, 1, 2, 3, those are going to be normal. I didn't draw the hydrogens in, but there's 3, 2, and 2 there. What really interests us is this carbon at the end. What is going on with that carbon at the end? Well, we say that we've got a positive formal charge there. If you remember how you got formal charges, okay, then that means that you take the normal number of valence electrons that it would have, which in carbon's case would be 4, right? It's a group 4 element. So you take the normal number that it has, and then you're going to subtract the number that it has in the actual problem. And bonds, remember, count as 1. Okay, so even though there are 2 electrons that make up a bond, we're going to assume that that atom gets half of that share, which means that it only counts each bond as 1. So what that means is that if carbon has a positive charge here, it has a carbocation, that means that technically what that means is that it only has 3 electrons around it in terms of the formal charge structure. Now, obviously, for there to be an octet and all that, those things differ. But what that means for us is that if it only has a share, if its share of the electrons is only 3, then what that means over here for this end is that I only have 2 hydrogens bonded to it instead of 3. How do I know that? 1, 2, 3 bonds, okay, 1, 2, 3. Each of those, it gets a share of 1. 4 minus 3, the 4 that it normally has, minus the 3 that it has given here, is what gives it that formal charge of that positive. And so what that means is that I've got to write my charge there. And so if we went back in and filled, okay, that is what that molecule looks like. So in the case of the carbocation, what is true is that I don't have any lone pairs, but I have a carbocation there of a positive charge, and so this is an exception in that I don't have 4 bonds on that carbon, I've only got 3. So that makes kind of good sense, that if we have 1 less electron giving us the positive charge, that I can't have quite as many bonds. What makes less sense sometimes is how does having a negative charge there also mean that I have less bonds? So let's look at that case. All right, so remember, this is what the carbon structure here is going to look like. I'm not drawing all the other hydrogens yet, but I will. So I know that has 3, that has 2, that has 3. I know that because those all need to have 4 bonds, right? So I could fill in the rest of those hydrogens. But what's going on here at this second carbon? Well, it's got a negative formal charge. And so a negative formal charge means then that when I do my formal charge calculation, my 4 minus something, that it's going to come out to be a -1, which means that it's got to be 4 minus 5 to give me the -1. Okay, so to give me that -1, the 4 minus 5, then what that means is that I've got one hydrogen bond, okay, not one hydrogen bond, one hydrogen bonded to that carbon, and I have a lone pair there. Now, how do I know that it's a lone pair, not a bond? Well, the lone pair is the only way that I can get the 5 there. If I had the bond like I did up here, then I wouldn't have a formal charge. It would have been 4 minus 4, and so everything would have worked out evenly. But for it to have this negative here, that means that I have to have a lone pair there. So what does then that mean to us? It means that if it's a carbon, it's normally got 4 bonds, and that's true 99.9% of the time, unless you see a formal charge. And then what does the formal charge mean? Well, the formal charge always means that it's going to have 3 bonds for the carbon, and then it could mean, in the case of a carbocation, that we have no lone pairs left, or in the case of the anion at the carbon atom, the negative formal charge, that I'm going to have 3 bonds and a lone pair there. All right, so let's look at an oxygen example, and then we're going to sort of make a quick little chart that'll sort of run through everything and hopefully help you to recognize those things when you look at them, rather than having to sort of break them down and draw them out every time. Here's the deal. When you first do them, you're probably going to have to break them down and draw them out a little bit, because that's how you're going to be sure that you're doing it correctly. As we move through and you've done hundreds of line structures, then hopefully that won't be as necessary. So what does this look like? So I've got a carbon, then I've got an oxygen down here. None of these carbons have a formal charge, so I can assume that they're saturated, meaning that they've got all of the hydrogens that they can hold. Okay, and so then the question comes down here for the oxygen. Well, if you've known from the structures that we've drawn already, oxygen is pretty likely to have some lone pairs. Okay, nitrogen is going to work the same way. It's pretty likely to have some lone pairs. So what then is going on in the case of this oxygen? Well, again, if we went back to the formal charge structure and tried to figure it out and said, okay, so this oxygen has a share of 1 bond, right? So that gives it 1 electron. And then how many other electrons does it have around it to get it to be negative? Well, what's the valence on oxygen normally? It's 6, right? It's a group 6 element. So it's going to, or group 16, depending on how you're covering it. So that means that has 6 valence electrons. So formal charge-wise, to get to a negative, that means that in this structure, it has to have 7 essentially accounted for it. So that means that the bond is 1 of the 7. And so to give it the other 6 I need to get to 7, it's going to have 1, 2, 3, 4, 5, 6, meaning that it's going to have to look like this. 1, 2, 3, 4, 5, 6. We're going to put the negative there. So that means that to get it to have a negative formal charge, it's going to have 3 lone pairs instead of the normal 2. Normally it has 2. And why does it normally have 2? Well, because in a normal situation, oxygen tends to form 2 bonds, whether that's a double bond, whether that's a bond to a carbon and then maybe to a hydrogen or something like that. So the formal charge should sort of indicate to you that it doesn't really have the normal amount of bonding that it would normally have. So in the case of oxygen and nitrogen, what that can mean for them, just as in the case of carbon, it can mean that they can have a different number of bonds than what they would typically have. And so I'm going to put up a quick chart and we're going to talk about that real quick. One thing before we jump into that real quick. So what we're starting to see here is that in order to show a mechanism, or really to show the structure or show what's going on in any real sense, we have to know one of 2 things. We have to know either what the formal charge is or what the lone pairs are. If we know one of them, we could then figure out the other. So if the lone pairs were given, you would use your normal formal charge rules to figure out what the formal charge is. If you see a formal charge given, you could then go back and figure out what the lone pairs were. So the question is, which of them do you write? Do you write both? I mean, this is correct. But obviously, we don't normally draw everything, right? The whole point of doing line structures is to sort of simplify things so that we're not writing as much. Well, here's the way it works. Organic chemists almost always put the formal charge instead of the lone pairs. And it comes down to the whole reason for line structures in the first place, which is that it's simpler. there are going to be a lot more lone pairs in a molecule than there are formal charges. So it's much easier to note the fewer formal charges in the molecule than it is to go back and write all of the lone pairs. Just always know that when you see a formal charge that you should get in your brain that I've got to start thinking about what's going on with lone pairs. So let's summarize the whole thing and let's introduce what's going on with the nitrogen as well so you can sort of see how the whole thing works out. Okay, so real quick, for carbon, we already talked about carbon. We went through the whole thing, so you saw what it looked like. But just to refresh your memory, if a carbon atom has a negative formal charge, it means that it's got 3 bonds and 1 lone pair. Obviously, the no charge structure is the norm, 4 bonds. And then if it's got a positive formal charge, it's going to have 3 bonds and no lone pairs because you've pulled an electron away. The others are shared in those 3 bonds that are left. That is useful to us because that tells us if we've got a formal charge, how many hydrogens and all that stuff gone there. So what about the others? What about nitrogen and oxygen? All right, so for oxygen, same scenario. We talked about the anionic state here. We already said that that's going to mean that it's got 1 bond. It's got 3 lone pairs. Again, formal charge-wise, that's what gives it the negative. The normal state for oxygen would be that you have 2 bonds and 2 lone pairs, meaning that that's the no charge state. That could be like a carbonyl group. It could be something like a hydroxyl group where it's bonded to a hydrogen. It could be in an ether where it's sort of the connector between 2 carbons. Any of that, that's the normal state. Oxygen typically has 2 bonds if there's no formal charge on it. And then if it has a positive formal charge, that would mean that it would have 3 bonds and 1 lone pair. Not really a great state for oxygen to be in. I don't want to use the word comfortable, but I mean like that state is not perhaps maybe quite as stable. Some things are going to need to happen to sort of relieve some of that. Oxygen is a period 2 element, and therefore there's only so much sort of space to move around those clouds in there. So that's oxygen. Let's talk about nitrogen. So the other example that you're likely to see and have to worry about lone pairs a lot is nitrogen. Okay, you'll recognize this is sort of the normal state that nitrogen is going to be in. 3 bonds. There's 1 lone pair on it. That is an ammonia. We're sort of used to seeing that. Another one that we really commonly see as well is our ammonium ion. Right, that's one of our cations. You remember that because you're like that was the polyatomic ion that actually had a positive charge. So here's why. 4 bonds in it, okay, means that the formal charge, nitrogen normally has 5 valence electrons. We subtract the 4 from the bonds. That gives it a positive charge. This actually happens a lot more than you might think. Nitrogen often forms some 4 bonds, but again, that's going to give it a formal charge. And then we've got the state where that nitrogen could just have 2 bonds in it and then have 2 lone pairs. That's perhaps a little less likely, much like the positive case in the oxygen perhaps is somewhat less likely. Okay, so that's lone pairs of formal charges. Remember that you should be able to interconvert them. Remember that ideally, if you're drawing a line structure, that you're going to draw the formal charge, you're going to put the formal charge on it, not draw out all the lone pairs, but you always need to be prepared to put in the lone pairs as necessary, recognizing them from the formal charge. Thanks, kiddos.